so if we have a beam with transverse loads, so like if you had something like a simply supported beam, and we applied a load in the center, we can account for the displacements and the stresses and the strains within this beam by using a finite element called the beam element. All right, so for the beam element, it has 2 degrees of freedom. It can it has a slope at each node, which is denoted with a theta I, or theta j, and it has a displacement, a vertical displacement at each node, vi and vj. Okay. All right, and at each node you can apply a transverse force, which we are denoting with a vi and vj. And we also have a concentrated moment, m of I and m of j. So, so within our element, we can define our displacement function of x, or vertical displacement, as being equal to this polynomial. All right, so it's just a cubic polynomial. We can then take the derivative of that polynomial with respect to x to determine the slope. All right, we'll get this function here. Okay, so we know that we can define the displacements, we can assume that we know the displacements and slopes at I and j. So we're going to assume we know the displacements at I and the displacements at j. So I is just the left-hand side of the element, and j is just the right-hand side of the element. All right, and then theta I and theta j is just the slope at the left-hand side of the element and the slope at the right-hand side of the element. Okay, so if we just plug in x is equal to 0 and x is equal to the elemental length, or the length of our element, we can solve for vi, vj, theta I, and theta j in terms of our constants, a0, a2, and a3. Okay, and then we can take these 4 equations and we can solve, we can rewrite them in this algebraic, we can rewrite, we can solve for a0, a1, a2, and a3. So if we do that, we can take our original equation for v of x, and we can plug in our unknowns, our values for it, for a0, a1, a2, and a3. Okay, so we can take our v of x equation now and we can rearrange it in terms of nodal displacements vi and vj and our nodal slopes sigma, theta I, and theta j. Okay, so everything else within these brackets are going to be our they're going to be our shape functions. So they're only a function of x and known constants. So we have our first shape function we'd write as n v of x of I, because it's on the left, it's due to on the left-hand side of the element. Our second shape function would be n theta of xi. our third shape function would be n v of x j, and then our last shape function would be nv or n theta of x j. We have four shape functions that are only functions of x that define our displacement as a function of our nodal displacements and nodal slopes. So we can rewrite this rewrite this just as an algebraic equation, where we just take our four shape functions as our coefficients of our displacements and slopes, and then we can rewrite this in if you prefer, in a matrix form, where we have our displacements and slopes as an array. We have our nodal, our shape functions, and our interpolation function, or our interpolation functions as an array. What we can then do is we can define our strain energy for a transversely loaded beam element to obtain the stiffness matrix here. Okay, so our stiffness matrix is just equal to, so because it's a transverse loading, our stiffness is going to be dependent on the elastic modulus, the moment of inertia of the element, and the length of the element cubed times these additional terms. So it's not really important. You don't really need to know how you can derive that stiffness element. All you need to know is that for this is the stiffness matrix. So we can use the Rayleigh-Ritz method and apply the total potential energy equation to obtain the following system of equations. So all we did here to attain is we can solve for the displacements, vi, theta I, v of j, and theta j, or the loads vi, the nodal transverse loads vi and vj, and the nodal couple moments mi and na. So this is our global stiffness. This is our system equation for a beam element. So that's how you define the stiffness matrix for a beam element. There's not really too much else here to go through. We'll talk about how you assemble a global stiffness matrix through a couple of example problems for the beam element